Can you imagine a factory that can consume more than 10,000 tons of steel and go from empty ground to full operation in under 2 years? And that's just the beginning. Inside Tesla's semi-factory, massive 4680 battery packs are being built, capable of delivering up to 1.2 megawatts of charging power, enough to power an entire neighborhood, all packed into a single truck. Before we go further, if you're new here, consider subscribing, turning on notifications, and sharing your thoughts in the comments. Tesla isn't thinking small either. They're aiming to produce up to 50,000 semi-trucks annually. So what's actually going on inside this factory? Why do the production lines seem so fast? And why are traditional trucking companies watching so closely? As you step inside, the first surprise isn't on the floor. It's above you. Tesla has turned the ceiling into an active part of the production system. Overhead carriers move entire vehicle modules weighing over 10,000 pounds, placing them with extreme precision, within half a millimeter. This isn't just impressive engineering. It eliminates major inefficiencies. There's no need for forklifts, cranes, or manual repositioning, which can take up a significant chunk of assembly time in traditional factories. Even more importantly, Tesla has expanded production into 3 dimensions. Instead of everything competing for floor space, they use vertical space too, reducing the overall factory footprint by up to 40% for the same output. That directly cuts costs, one of the toughest challenges in automotive manufacturing. Workflow efficiency also improves dramatically. With components suspended, both workers and robots can access them from all angles at once. There's no need to rotate parts or wait for access, which boosts productivity and reduces idle time without requiring people to work faster. And then there's resilience. If one station has a problem, the system doesn't stop, it adapts. Modules can be rerouted around issues, keeping production moving. This flexibility helps Tesla aim for over 90% operational efficiency, compared to the 75 to 85% range typical in traditional plants. It raises an interesting question. If production can move around problems instead of stopping for them, is it even a traditional assembly line anymore? As you go deeper, something even more fundamental changes. For over a century, vehicles have been built step by step in a straight line. One delay could halt everything. Tesla has moved away from that model entirely. Instead, they use a modular parallel system. Different parts of the vehicle, like the cabin, chassis, drivetrain, and battery, are built simultaneously in separate areas, only coming together at the final stage. This completely changes how production scales. Work no longer queues behind previous steps, and multiple teams can operate at the same time. Instead of making lines longer or faster, which is expensive and fragile, Tesla can simply add more parallel modules to increase output. That's how they plan to produce tens of thousands of trucks each year, with long-term goals of reaching around 50,000 units annually without hitting the same physical limits as traditional manufacturers. But this also leads to a bigger question. If production becomes parallel instead of sequential, what really limits manufacturing speed? Further inside, you reach what used to be Tesla's biggest bottleneck, battery supply. For years, delays weren't about design, but energy storage. Now, that challenge has been largely solved. Tesla produces its 4680 battery cells directly at Gigafactory Nevada and feeds them into the production line almost in real time. They've also introduced dry electrode technology, which significantly reduces energy use, cuts equipment costs by up to half, and shrinks the factory space needed for battery production by as much as 70%. The result is clear: higher production capacity and lower cost per kilowatt hour. This makes large-scale electric trucks economically viable, especially with battery packs estimated between 800 and 1,000 kilowatt hours. That's the difference between a niche product and a truly competitive mass-market platform. And Tesla isn't just adding batteries into trucks, they're designing the entire vehicle around them. The Tesla Semi is built with 3 battery packs positioned low between the axles, which lowers its center of gravity by about 20% compared to traditional diesel trucks. This design greatly improves stability and reduces the risk of rollovers, an important factor, especially since jackknifing contributes to a significant portion of heavy truck accidents. As you move toward the end of the production line, Tesla introduces something many manufacturers tend to avoid: extreme real-world validation. Every Semi is tested under megawatt-level charging conditions, reaching up to around 1.2 megawatts. This isn't just a simulation, it's a full stress test. At that level of power, managing heat becomes a major challenge. Everything is pushed to its limits, from thermal systems to connector durability and overall stability. Each truck goes through this process before delivery, and the results are crucial for real-world use. The Semi can charge from about 5% to 70% in roughly 30 minutes, which aligns perfectly with mandatory driver rest breaks during long-haul routes. This makes electric trucking practical without disrupting existing logistics schedules. On top of that, regenerative braking handles up to 80% of the braking force. This significantly reduces wear on traditional brakes, extending their lifespan by 2 to 3 times. In an industry where downtime can cost thousands of dollars per truck each day, that kind of reliability makes a big difference. Tesla isn't just asking whether the truck works, they're ensuring it can handle worst-case scenarios before it ever leaves the factory. Now step outside for a moment, because the next innovation isn't confined within the building. The Semi Factory and Gigafactory Nevada operate as one continuous system, not for convenience, but to eliminate delays. Components like battery cells, stamped metal parts, and molded pieces don't sit in storage or wait to be shipped. Instead, they move directly from production into assembly. This approach removes the need for warehouses, inventory buffers, and transport delays. In traditional manufacturing, parts can sit unused for days or even weeks. Here, Tesla aims for near-zero delay, where components flow seamlessly from one stage to the next without interruption. The result is the elimination of non-productive time, those periods where nothing is being built, yet costs continue to rise. Essentially, 2 factories function as a single synchronized machine. Back inside, you'll notice the robots, but they're different from what you might expect. Traditional automotive robots are designed for one fixed task. Tesla, however, uses more adaptable systems. These robots can switch tools, take on different roles, and evolve alongside the product. This flexibility is more important than it might seem. Vehicle designs change frequently, and in most factories, that requires costly and time-consuming retooling. Here, robots can simply be reprogrammed instead of replaced, allowing production lines to adapt quickly and efficiently. This turns the factory into something dynamic, a programmable system rather than a fixed asset. When you step back and look at the bigger picture, the 3D production system, parallel assembly, real-time supply integration, in-house battery production, megawatt-level testing, adaptive robotics, and continuous design improvements, you start to see something deeper. This isn't just a more efficient factory. It's a system built to eliminate delays, reduce costs, and scale faster than anything currently seen in heavy industry. Which raises a bigger question. If this kind of system expands globally, what happens to an entire industry built on slower, more rigid, and more expensive methods? To truly understand how the Tesla Semi is built, you have to move beyond the traditional assembly line model popularized by Henry Ford. Tesla's factory isn't a straight line. It's a 3-dimensional system designed to compress time, space, and cost. The first stage focuses on the cabin. Instead of starting with a bare frame moving slowly along a conveyor, Tesla begins by assembling the cabin as a nearly complete module. This includes the structural frame, mounting points, and early system integration. By doing this early in the process, Tesla removes one of the most complex and delay-prone steps from the main assembly flow. But here's where it gets interesting. Once the cabin is ready, it doesn't stay on the ground. It's lifted into an overhead carrier system. That single choice changes everything. In traditional factories, large components take up valuable floor space and create bottlenecks. Tesla, however, shifts that complexity upward using vertical space instead of crowding the floor. The result is smoother movement, fewer delays, and reduced idle time between production stages. And this leads directly to the system that makes it all possible. The next stage is what you might call a flying production line, a fully three-dimensional logistics system. Look up, and you'll see the true backbone of the factory in action. Inside the factory, massive suspended carriers move heavy assemblies, some weighing over 10,000 pounds, about 4,500 kilograms, through a continuous loop above the floor. But they don't just transport parts. These systems place each module with incredible precision, down to about 0.5 millimeter, removing the need for forklifts, cranes, or manual alignment altogether. Think about what that means in a real factory setting. In a traditional truck plant, repositioning a large component can take several minutes and require multiple workers. Here, it happens automatically, with carriers moving at speeds of around 1 to 2 meters per second. This alone can dramatically improve how quickly parts move between stations. Even more important is accessibility. Because components are suspended, both workers and robots can approach them from every angle: top, bottom, sides, front, and rear at the same time. Tesla estimates this reduces assembly time per station by roughly 20 to 25%. Not because anyone is working faster, but because waiting time is almost eliminated. Then there's one of the most overlooked advantages: resilience. If a station encounters a problem, production doesn't come to a halt. The system adapts. Modules can be rerouted or shifted to parallel lines, keeping the process moving. This helps maintain overall equipment effectiveness, OEE, at around or above 90%, a level most traditional automotive plants struggle to achieve. But efficient movement is only part of the story. The real question is, what are these parts turning into? This brings us to the next stage: the battery integration, which forms the structural core of the truck. At a dedicated station, 3 large battery packs are installed directly into the chassis. Unlike flat battery layouts used in many passenger EVs, the Semi uses more compact, cube-like packs designed to maximize energy within a limited space. Each truck uses 3 of these packs working together, delivering enough energy for an estimated range of up to 800 kilometers, around 500 miles, in the long-range version. This isn't just a specification. It shapes the entire design of the vehicle. The installation process is highly precise. Specialized tools secure the battery packs with exact force to ensure structural strength under heavy loads. Because of their weight, the placement of these batteries directly impacts balance, stability, and handling. That's the key idea. The battery isn't just a power source. It's a core part of the vehicle's structure. Everything from the frame to the suspension is designed around it. Once this energy foundation is in place, the rest of the truck begins to come together. Next comes modular assembly, where Tesla builds in parallel instead of following a strict sequence. Rather than adding thousands of small components one at a time, the factory assembles large subsystems independently, things like drive axles, steering units, pneumatic systems, and structural sections. This approach significantly reduces the number of steps involved. In traditional manufacturing, there can be hundreds of sequential operations. Here, many processes happen at the same time in different zones. The benefits are clear. Fewer steps mean fewer opportunities for errors, faster production cycles, and easier automation. It also makes scaling much more efficient. Instead of extending a single production line, Tesla can simply replicate module stations to increase output. That's one reason the factory aims to produce tens of thousands of trucks each year, with long-term goals of around 50,000 units annually. As the truck nears completion, the focus shifts from assembly to durability. In the coating and finishing stage, the goal isn't just appearance, it's long-term performance. Unlike passenger cars, trucks operate under constant stress, traveling long distances in tough conditions. Each semi is treated with corrosion-resistant coatings designed to handle years of heavy-duty use. The materials and methods used here are closer to industrial-grade standards than typical consumer vehicle finishes. This ensures the truck maintains its structural integrity over hundreds of thousands of miles. In the logistics world, downtime doesn't just cause inconvenience, it leads directly to financial losses. Finally, before any truck leaves the factory, it undergoes a detailed quality inspection. At the end of the line, every vehicle passes through a high-intensity inspection system known as a light tunnel. This environment uses bright, controlled lighting to reveal even the smallest surface imperfections, defects that might not be visible under normal conditions. This final inspection stage isn't just about how the truck looks, it's about maintaining consistent quality at scale, which is one of the toughest challenges in manufacturing. The system works as both a filter and a feedback loop. It catches defects before delivery and sends that data back into the production process to continuously improve it. It also represents something important. After moving through a fast, highly automated system, this is the point where everything is carefully checked and confirmed. Only then is the product ready to fulfill its real purpose, not inside the factory, but out on the road. That leads to the final stage, the driving experience, where manufacturing meets real-world performance. How the semi is built directly shapes how it drives. Thanks to electric motors, it delivers instant torque, meaning there's no delay when accelerating, no gear shifts, no lag. Even when carrying loads of up to 40,000 pounds, around 18,000 kilograms, the acceleration remains smooth and controlled. Efficiency is another key advantage. Real-world estimates suggest energy consumption of about 1.7 to 1.8 kilowatt-hours per mile, which translates to significantly lower operating costs compared to diesel trucks on a per-mile basis. Regenerative braking plays a big role as well. It not only recovers energy but also reduces wear on traditional braking systems, extending their lifespan and reducing maintenance needs. Combined with fewer moving parts overall, this leads to higher uptime, something fleet operators care deeply about. Inside the cabin, the experience is also very different. It's much quieter, which helps reduce driver fatigue during long trips. The central seating position, along with multiple exterior cameras, improves visibility and minimizes blind spots, one of the major causes of trucking accidents. Just as important, the system simplifies driving. There's no need for gear shifting or complex engine braking controls. This makes the truck easier to operate, shortens training time, and reduces the chances of human error. What you're looking at isn't a traditional factory process. It's a system designed for speed, flexibility, and scalability. By combining 3D logistics, modular assembly, and integrated battery design, Tesla has built something fundamentally different.